Mr. Heffernan here. Here's a short video on the index of refraction and Snell's law. So first example here, just calculating the index of refraction. So here we have the speed of light in a vacuum is 2.9979 times 10 to the 8 meters per second, almost 300 million meters per second. And if a ray of light travels from the vacuum of space, and air is almost the same thing really, and runs into a dilithium crystal wall, it's going to slow down to 1.225 times 10 to the 8 meters per second. So by what factor does the dilithium slow down the light? So what's the index of refraction? So here we're going to use this formula right here. So your index of refraction, N, is equal to the speed of light in a vacuum, C, divided by V, the speed of light inside your medium. So we're just going to use this formula right here. Okay, so let's just double click on that. Alright, so to find out the value, we're going to type in the speed of light in a vacuum, 2.9979 times 10 to the power of 8 meters per second. Alright, there we go. Alright, and we need the speed of light inside our medium, which was 1.225, so 1.225, okay, times 10 to the 8 meters per second. Now, if you really need to see this in standard notation, it looks like this. So that's going to be equal to 299,790,000 meters per second. Okay. Divided by, oops, there we go, 125,500,000 meters per second. You see why we like to use scientific notation, a lot less zeros. So we're going to simplify this a little bit. So these 10 to the 8s, don't really need them. 10 to the 8 divided by 10 to the 8 is just going to cancel out to be 1. So that's the nice thing about speed of light not really slowing down that much, I guess. And so on your calculator here, you can just do that calculation. 2.9979 divided by 1.225, and we get 2.45 approximately. So 2.45. So 2.45 is the index of refraction for dilithium. Okay, so now that means the index of refraction is, there we go, is 2.45. So light or radio or any EM wave will slow down by a factor of 2.45 times when it enters this medium. Okay, so if you go from the vacuum of space into this medium, you're going to slow down quite a lot. Okay. So that's the index of refraction calculation. Another useful one is when a ray or when a beam of light comes from one medium to the other, it's going to refract or bend and change direction. Now, if you go from low density to a high density, it'll bend towards the normal, so you get a smaller angle. And if you did this backwards, you went from a high density to a low density, you would bend even further away from the normal. So here we got some water and we have some crown glass. So the index of refraction for water is 1.33, and for glass it's 1.52. And we're going to have a ray of light, so this yellow ray of light is going to come in at a 30-degree angle, and we just want to know, okay, what angle is it going to come out at? So that's what we're trying to find out. Okay, I'm just going to bring this angle thing over here, and we're going to try to find out what this angle is right here. So Snell's law is pretty easy. Your incident index of refraction times the sine of the incident angle is equal to the refractive index of refraction times the sine of its angle. So we're just going to use this formula right here. So let's go into this. Alright, so we start off with an index of refraction of 1.33 for water, and we're coming in at a 30-degree angle. So let's pop that in. And we're going into glass, which is 1.52 for its index of refraction. Okay, so all we got to do now is just isolate the theta. So the first thing I do is I cross multiply the 1.52 over to the other side. Alright, so we're just going to bring it over like this. Okay. Now technically, this is technically sine to the positive 1. So if you want to bring sine to the positive 1 over to the other side, you also do the opposite, which is negative 1. So when I bring the sine over to isolate my my theta, my angle, I'm going to use a minus 1 there instead. Okay, and that gets rid of the sine or sin. Okay. All right. So on my calculator, if I want to find out what my angle of my angle is going to be when it goes in through the glass, that's going to be what? So on your calculator, if you have a good calculator, you can go 1.33 sine 30, it equals, divide by 1.52, it equals, shift sine, answer, bang, 25.9 degrees. Alright, that's what I'm going to get from my answer. Now if you have a poor calculator, you have to do things backwards. You'll have to go 30 sine, it equals, multiply by 1.33, hit equals, divide by 1.52, hit equals, shift or second function sine, answer, and equals. And you'll get the same answer. So if you have a good calculator, you can do what you see. If you have a poor calculator, just do things backwards, and you should get this answer. So try it out. If you don't get this answer, maybe contact me and have me do a Zoom with you on how to use your calculator. Okay. So that's the answer for that. There we go. Oops, moved my whole picture down on me. Alright, let's just fix that for a quick second here. And back up here. There we go. I guess the 30 wants to stay there. Oh well. So, now what we're going to do is one more problem. We're going to do, oops. Okay, well, whatever. It's a 30-degree angle going in, comes out at 25.9. The other problem you might come across is total internal reflection at a critical angle. So for example, let's say this is diamond, and we come in at a special angle called the critical angle. What will happen is the refraction will actually be 90 degrees, which means it will stop refracting, and it will actually 100% reflect. So this refraction line, I will just kill it, because once you hit 90 degrees of refraction, you're not really refracting, you're just reflecting at this point in time. So that is how you're going to solve this, knowing that diamond has a index of refraction of 2.42, and we're going into water, 1.33, and we know it's going to be refracting at 90 degrees. There we go. Now sine 90 is effectively 1, so that makes life easy. So that's just going to be times 1 here. So there we go. And so now to find the theta, the critical angle, so I'm just going to rename this crit for critical angle. I'm just going to divide the 2.42 over to the other side. So we'll just do that. So I'm going to bring the 2.42 over. There we go. And technically this is a sine to the plus 1. So all I got to do is to bring it over is make it a sine to the minus 1. So I'm just going to bring it over like this and turn it into a minus 1. There we go. Like that. And I don't really need this 1 anymore. It's kind of pointless. There we go. So on my calculator, I'm just going to go shift sine brackets. Exactly what you see in an equation. 1.33 divided by 2.42. Close my bracket and hit equals. And it'll give me a critical angle of, I'll just write it down here, 33.3 degrees. Now if you have a poor calculator, one of those cheap backwards calculators, you'll have to do this backwards. You'll go 1.33 divided by 2.42, hit equals, and then you'll go either shift or second function, whatever your calculator has, sine, and it'll give you the 33.3 degrees. Okay. If you have a good calculator, you can type in exactly what you see, and if you have a poor calculator, well, just do it backwards. Okay. There we go. All right, so anytime you go from diamond into water, if you come in at a 33-degree angle, that is going to make it come out at a, let's just put it right here, there we go. It's going to make it come out at a total internal reflection of, if it comes in at a 33.3, it'll bounce off at a 33.3, and technically the refraction is 90, so it just doesn't happen. Okay, so there you go. That's everything you need to know for index of refraction and Snell's law. Good luck.